Hi everyone, welcome back to Math 261. This is Scott. Let's get started. So now we are embarking on the phase 3 of our conquest of determinants. So 3.1, we asked how do we actually calculate a determinant. In 3.2, we figured out what a determinant actually determines. And now, in section 3.3, we're going to look at some assorted applications of determinants. In other words, why. So 3.3 has to do with applications of determinants. In particular, Cramer's rule, volume, and linear transformations. Alright, so let's start with Cramer's rule. So this is a specific way that you can find solutions to a linear equation or system of linear equations, and in particular, it is useful in very specific contexts. So this is another way to solve linear systems. Now, this may seem unnecessary, and for the most part it is, because the row reduction technique that we've been doing is actually it's the gold standard of ways to solve systems of equations. However, if what we're talking about is very specific cases, Cramer's rule is sometimes quicker and oftentimes a lot easier to do than row reduction. So this is specifically useful to solve 2 by 2, by which I mean a system of two variables, or two equations and two variables. Specifically useful to solve 2 by 2 systems, or systems with complicated coefficients. In particular, such as complex numbers, or algebraic expressions. So here's how it works. So some notation. We will write A. I guess we should say up here, the setup for this whole section is that A is n by n. That's a setup for all of chapter 3. We're always talking about square matrices in chapter 3. So A I of B. So what this represents is you take the matrix A and you replace column I with the vector B. So take A and replace column I with the vector B. So for example, if A was equal to, let's say, like 3, 2, is equal to 1 and -3, say. Then AI, or actually I should specify A1 of B would be take column 1 and replace it by B. So 1, -3 to -5, and A2 of B would be then 3, 1, 1, -3. Then here's Cramer's rule. So in order for this to work, A has to be invertible. So if A is invertible, which means, among other things, that its determinant is not 0, and it means that the system AX equals B will have a unique solution, and blah, blah, blah. And then what we're going to get here is is a formula for that unique solution. So if A is invertible, then the solution to AX equals B is x1 is equal to the determinant of A1, A1 of B over the determinant of just A, x2 is equal to the determinant of A2 of B divided by the determinant of just A. And if there are any more variables, which we won't usually use Cramer's rule for more than 2 variables, but there's no law against it. So if there were any more variables, it would continue. It would go like that. So each one, xi, is equal to the determinant of ai of b divided by the determinant of a. So as an example, solve using Cramer's rule. And let's say what we had was, and if it's only 2 by 2, frequently instead of x1 and x2, we'll just write x and y. So let's say we'll just take this very one. So 3x plus 2y equals 1, and 1x, so just x, minus 5y is equal to -3. Now, would this be hard to row reduce? No, it would not. But it's also very quick and easy to solve this with Cramer's rule. So then A is, you just peel off the coordinates there, or the coefficients there, so 3, 1, 2, -5, just as above here. B would be the 1, -3, just as above there. And then important things we need to know. So the determinant of A, something we need. So this would be 3 times -5 is -15, minus 2 is -17. And furthermore, if I have A1 of B, that's going to be, as we just said, 1, -3 to -5, which means that the determinant of A1 of B is going to be equal to, so you do 1 times -5 is -5, minus -6, so plus 6, so it's going to be 1. And then here we'll have a 2 of B, which is 3, 1, and then 1, -3, which then means the determinant of a2 of b. And we just do the usual thing. We get negative 9 minus 1 is negative 10. So then, solution. x1 is equal to 1 over negative 17. And x2 is equal to negative 10 over negative 17. So in other words, x is equal to negative 1/17 and 10/17. The negatives cancel. Or you could write that, and commonly would be written as where you pull out that denominator. So 1/17, negative 1/10. All right, so there it is. Now, could we have done this by row reducing? Yes, we certainly could have. Could we have done it by any other means of solving a system of equations? Yes, we certainly could have. And it would have been easy because this was just a 2 by 2 system. However, seeing a number like 17ths tells you that whatever you were going to do was going to involve some ungainly fractions, and we at least saved ourselves the anguish of that. You can see how the 17 was going to come in. It's going to be, so we're going to subtract, say, 3 times this from this. That's going to be negative. So it's going to be negative 3 times this. So it's going to be positive 17y equals, and then that's going to be 10. And you can see how that would shake out. But it wasn't so hard. It wasn't so hard to do it this way. Wouldn't be too hard to do it any other way. Now here is where this comes into use. So here's an application of this. So again, this is an application that comes up big time in Math 256 in a lot of ways. Everything in this class is more or less foreshadowing for something important that's going to happen in Math 256. But when you are solving systems of linear differential equations, then a method that's frequently used is Laplace transforms. So Laplace transforms are used to solve systems of differential equations. This is in Math 256. And when you do this method, this will produce things that have coefficients on the variables that will be algebraic. They'll have s's in them. So there are systems with coefficients involving a parameter s, or really it's an indeterminate, but that's all right. So this is an example that literally I just pulled up from an example that was done in Math 256. So in Math 256, you can have a system such as this. So we can have a system like this, and the way it's usually written, so we'll have s minus 1, then there's a capital X, minus, say, 2y, and that equals 0. And then another one would be, the other equation would be negative x plus sy is equal to 1 over s plus 1. These are s's, not 5's, s's. So there is so the coefficients of the x and the y, which are the actual variables in this thing, they involve a little dummy parameter of s. and you'll see in Math 256 what this comes from. Also, those of you who have dabbled in circuits may have already seen this, or if you haven't, you will soon. Laplace transforms are very heavily used in problems that involve circuits and other kinds of electrical systems that all come into the heading of certain very stereotyped categories of differential equations. And those stereotyped categories of differential equations are very handily solved by the method of Laplace transforms, and that's really why I'm bringing it up. It's mostly useful in electrical circuit type equations. So using Kirchhoff's laws, you get a differential equation that involves a form that is called linear, and then you can do a Laplace transform to produce this. And the goal is you want to solve this for the x and the y in terms of s. So then here, now a is equal to s minus 1, negative 2, negative 1, and s, and b is going to be 0 and 1 over s plus 1. So then, that means the determinant of A will be s times s minus 1 minus negative 2, so, sorry, actually minus, so it's still going to be minus 2. And so if we simplify that a little bit, it's just going to be s squared minus s minus 2, which we would then want to factor if we could, and we can. So it's going to be s minus 2 times s plus 1. So that's the determinant of A. Now, A1 of B, so that's going to be a part of it. Now A1 of B is going to be 0, 1 over s plus 1, and then negative 2, and then an s, which means the determinant of A1 of B is going to be 0 times s minus negative 2, so it's going to be positive 2 over s plus 1, and also A2 of B is going to be s minus 1, negative 1, and then over here we're going to have 0 and a 1 over s plus 1. So then the determinant of A2 of B is going to equal, so it's going to be, looks like s minus 1 over s plus 1, and then minus 0 plus 0, I guess. So then, that gives us our x and our y. So x is equal to, by Cramer's rule, which in this case is going to be, so it's going to be 2 over s plus 1, all divided by s minus 2 times s plus 1, which you can rewrite let's say you multiply the top and bottom by s plus 1. Which you can then simplify to make 2 divided by s plus 1 squared s minus 2. Now, on the other hand, y is going to be the determinant of a2 of b divided by the determinant of a, which is going to be the s minus 1 over s plus 1 divided by s minus 2 times s plus 1. And here I'll put parentheses to indicate exactly where these divisions are happening. And so by the same logic, that's going to be s minus 1 over s plus 1 squared times s minus 2. So, if this were a differential equations class, this would be the first step towards dealing with a system, maybe an electrical circuit or maybe a spring type system. And what you would then do after that is you would have to use actually the technique of partial fractions to separate these pieces out, and then you would then be able to apply the inverse Laplace transform and get an answer. But just to show you that this is not a bluff, this literally was an example from Math 256. So I'll show you the page of notes. So this really was the page of notes for Math 256. So I skipped us down to the part where we actually entered the scene, but literally this was an example straight from the pages of Math 256. So that's a technique that will come in handy sometimes for very specific kinds of circumstances. But its usefulness is a bit limited because row reduction is already the best way to solve systems of equations in most cases. The differences or the exceptions are if it's 2 by 2, Cramer's rule can save you some issues with weird fractions, and it can help deal with situations where your coefficients are a little bit unorthodox. Maybe they're complex numbers, maybe they're algebraic expressions, things like that. So that's Cramer's rule. Now, the other parts of this section that are of use to us are volume and linear transformations. So let's talk about what a determinant actually means. So the geometric meaning of a determinant. So we already learned why it's called a determinant. It's because it's important for determining whether the matrix has certain properties. Now, there's also an actual meaning to the number that you get, besides it just being 0 or not, and that meaning is it actually has to do with the volume of certain figures in space. So for a 2 by 2 matrix, let's say that the 2 by 2 matrix is something like this. So 2 by 2 case. For 2 by 2 matrices, let's say that A is equal to U and V. So in other words, I'm representing the columns of A by a U and a V. So then the determinant of A, if we then take the absolute value of that, because we're not interested in having a negative volume, so the determinant of A gives the area of the parallelogram formed by the vectors U and V and coming from the origin. So in particular here, we have a matrix. The matrix is two vectors. The columns of the matrix are two vectors. So then, let's say that U is pointing like this, and V is pointing like this. Then we can make a parallelogram out of that. With a displaced copy of U and a displaced copy of V. And here, actually, it should go a little bit more like that, and a little bit more like that. And then the area of this. So the area is the absolute value of the determinant of the matrix whose columns are U and V. Now, that's what the case is if it's 2 by 2. But if it's 3 by 3, then we have to move up one dimension, and so we're no longer talking about an area, but now we're talking about a volume. So 3 by 3 matrices. So we're going to have A. Let's say the columns of A are the vectors U, V, and W. And then the determinant of A, the absolute value of that, gives not the area, but the volume of, and it's not a parallelogram anymore. Once it's three-dimensional, then it becomes what's called a parallel pipette. So it's like a three-dimensional version of a parallelogram, parallel pipette, formed by U, V, and W. Coming out of the origin. So as an example, just to see a sketch of this, let's say that we had U and it was going like that. Let's say that we had a V that was going like that. Say that's going into the page. And then we had a W that was coming up like that. And I don't want to bog us down too much with drawing axes or anything. We just want a general picture here. So then the parallel pipette that we'd be talking about would be the one that would be formed just by continuing each of these vectors in each of these ways. So then what else do we got here? We got still this one to this one and down. So then the volume of this is the absolute value of the determinant the matrix whose columns are U, V, and W. And the same thing would actually still carry forward in higher dimensions as well. Just the difference is that it no longer has the same intuitive meaning to us as a three-dimensional volume does. It's just a 4-volume or 5-volume and so on. So it becomes, or a hypervolume sometimes it's called. So it would still be the same geometrically, but it would be carried out in a higher dimension. Now note, because A transpose and A have the same determinant, we could have also used the vectors as the rows. We could also have used the vectors as rows instead of columns in both of the above. So it could have been rows instead of columns, no difference, because A transpose and A have the same determinant. So, as an example, find the volume of the parallel pipette with a vertex at the origin and adjacent vertices. So this is just so you can see how these problems are worded. And adjacent vertices at, and I'll give you these as points, like three-dimensional points. Say 1, 0, -2, 0, 3, 4, and 1, 1, 1. So in other words, it's giving us 3 points in 3 space, and it's just up to us to find the volume of the associated parallel pipette, and there's no point even in trying to draw this because it's too time consuming. We can just cut to the chase. So we can just take A to B, the matrix, and here the first column is just going to be that point, 1, 0, -2. When it comes to space and vectors, you can consider a vector to be the same thing as essentially a point. So a position vector is another way of thinking about a point, and it's basically a displacement vector from the origin towards that point. So points and column vectors are basically the same thing in a lot of contexts. So 0, 3, and 4, or at least they can be, you can translate between them pretty easily. And then 1, 1, 1. All right, so then the volume is equal to the determinant of A, which is equal to 1, 0, -2, 0, 3, 4, 1, 1, 1. And now we pick our favorite row or column to expand along, and here, I like the look of that first column. Also, the first first columns and first rows have a natural advantage in that the checkerboard is easiest with them. So we have the checkerboard plus, minus, plus, and the rest of it is not really necessary, but it doesn't hurt anything. Checkerboards are nice and easy. Just remember it's always a plus in the upper left. Okay, so it's going to be 1 times, and then we have 3, 1, 4, 1. And then it's going to be minus 0, and then it's going to be plus negative 2 times 0, 1, 3, 1. Okay, so it's going to be 3 minus 4 times 1 is negative 1, minus 0, and here we're going to have negative 2 times 0 minus 3, so it's going to be positive 6. So then the overall result will be 5, which means the volume will be 5 cubic units. Whatever the units of this would be, it's 5 of those cubically. And we would, technically this is the absolute value of the determinant of A. So if this had come out negative, we would just change it to positive. So technically, when we are doing this kind of calculation, we are talking about actually a signed volume, not so it's not quite the same thing as a volume in the usual sense, because mathematically from the determinant a negative could have come out. But if we want to think of it as regular volume, then we have to take the absolute value. So what the sign of the volume would mean, if we were interested in that, is basically if you go from U to V, is W pointing in the direction that the right-hand rule would be determining. So it doesn't have to be pointing exactly perpendicularly, but it does need to be more on that side than the other side. So it's basically like so if we were to go from U to V, is the volume here above that or below that, is what the sign of the volume would indicate. But that's not typically what we are interested in when we're talking about volume, because we typically just mean the geometric interpretation, which is how much stuff. So that's volume and Cramer's rule. And now for the third piece of this section, linear transformations. So if we have a linear transformation that can be represented by a square matrix, so if T is mapping from Rn to Rn, and T of x is A of x, where A is, as usual, n by n, then what does the determinant of A mean? Well, the absolute value of the determinant of A gives the factor by which T changes the volume, and it might be a hypervolume depending on the number of dimensions. So volume or area or whatever the appropriate word is for the correct number of dimensions changes the volume of a region. So for example, if T is going from R2 to R2, and let's say and the determinant of A, I should say, absolute value of that is 2, then that means that if you were to take any image, or if you were to take any figure in R2, it's like a shape, like a circle or a square or any type of shape, and you were to apply T to it, then that region would have its area doubled. So then T would transform a plane figure to another one of twice the area. Okay, so this is not something that is of extreme importance to us to deal with right now, but what I do want to mention about this is the relationship that it has with the invertibility. So the invertible matrix theorem in its new determinant setting says that if the determinant is 0, then the matrix is not invertible. And what that means here is, if the determinant is 0, that means we are transforming the plane figure into something of area 0, which is, in other words, just like a little line segment or something. And we can't undo that, because it's like trying to get a figure from a shadow. There are too many ways it could have been collapsed down. So you're basically losing one dimension when you're applying this transformation. So that is that. So that's it for Chapter 3, and that's it for this installment of Math 261. Join me for the next episode, in which we will start talking about Chapter 4. So until then, bye.